there's one more concept that I need to teach you guys in order to fully be able to dive into conservation of momentum problems. And this concept is a distinction between two types of collisions, elastic and inelastic. Okay, I'll write these guys down. So we have elastic collisions and inelastic collisions. Okay, so in an elastic collision, all right, kinetic energy is always conserved, right? In other words, no energy is lost to heat or sound or anything else. No energy is lost to the universe before the collision and after the collision. The kinetic energy of both objects, the sum of it, has to be the same before and after. That is an elastic collision, okay? The important thing to tell you about elastic collisions is that they are an idealization that does not fully correspond with what we see in the real world, okay? Obviously, anytime you see a collision, you hear sound, right? That's energy that's leaving, right? It feels a little bit warmer, right? These guys feel a little bit warmer after they collide with each other. That's thermal energy being released to the world, okay? So you cannot say that in such a collision, in any collision in the real world, kinetic energy is perfectly conserved, right? But there are certain situations where it gets pretty dang close, and close enough where we can make an approximation and say that energy is conserved, okay? So just know that this is an idealization. Elastic collisions are an idealization, but sometimes we use them in physics because it makes our life a little bit easier, okay? And it's close enough to what's actually happening. All right. In inelastic collisions, it's different. Kinetic energy, as you can imagine, is not conserved, right? This is a real type of collision in the real world, right? In the real world, there's always going to be some amount of energy that's being lost, okay? Now, what do these two different types of collisions have in common? Well, in both, momentum is still conserved. So even if energy is not conserved in a collision, momentum is conserved in both. That's cool. I mentioned before that in some ways, momentum conservation is even more sacred than energy conservation. And that's because that no matter what kind of collision that you have, momentum is still conserved, even if we do lose energy to the universe. Okay? That's kind of cool. It's kind of powerful. It lets us know that there's something very, very solid. We're on solid ground when we're conserving momentum in a certain problem. Now, one classic example of an inelastic collision. So in many of the problems that you do in the book, you're going to have to decide, is energy conserved? Because sometimes you might have to conserve energy as well as momentum in a problem. And you need to ask yourself, is energy not conserved? Do I not have that available to me as a tool when I'm solving a problem? Okay. Most of the time, a question in a book or on the MCAT or on my exam will tell you if it's an elastic or an inelastic collision, right? But it's helpful to sometimes know for sure if something is an inelastic collision or not, even if they don't tell you. And one way you know for sure is anytime you have two objects, right, that collide, and then they end up sticking together, okay? That is always going to be an inelastic collision. As you can see in this one example on our slides, it says one common example of an inelastic collision is when the colliding objects stick together. In this situation, you absolutely know the collision is inelastic and kinetic energy is not conserved. And so it shows this example of two football players barreling and then sticking together and then falling to the ground. That is a collision you can be sure is inelastic. And I bring up this specific example because I feel like they show up quite a bit. Examples of collisions where, you have a bullet in a block and then the bullet gets stuck in the block, right? Or you have, a soccer player comes up and tackles another soccer player, right? Or you have, somebody throws some putty add another piece of putty and they stick together, right? And they go off and move together. Or opposite of that, right? You have, something that was together originally, like let's say an explosive of some kind, and it explodes in the sky, right? That's also inelastic because, it was stuck together at first and then separated. All right. So take this on to the misconception question that follows. It says, in the space shuttle, and this is a perfect example of what I was just talking about. In the space shuttle, in a circular orbit around the Earth, the shuttle collides with an asteroid that ends up in the shuttle's storage bay. Okay, so in other words, we have a situation where, like, here is the shuttle, right? Here is like the storage bay, right? And a little asteroid comes in, woo, right? And it ends up going into the storage bay, so that if this is before, then your after is going to be the shuttle, and then the asteroid's in the storage bay. All right? This is exactly what we were just talking about. Two separate objects before the collision, and then after the collision, they're one and the same. They are part and parcel, right? So which one of these statements do we know for sure? Only momentum is conserved? Yeah, probably, right? We'll check out the other answers, but yeah, momentum is going to be conserved, and we know that kinetic energy won't be conserved because it's an inelastic collision, because the two colliding things merge together. Only kinetic energy is conserved? No, not true. C, both momentum and kinetic energy is conserved. That's only true in an elastic collision. And neither momentum nor kinetic energy is conserved. No, momentum is always conserved in collisions, right? That's our sacred law. Okay? So now that we know these two different types of collisions, elastic and inelastic, and now that we know that energy is only conserved in elastic collisions, but momentum is conserved with both, we can move on to solve, basically any conservation of momentum problem that I could throw at you. And I'm excited to do that in the next video. Just one recap here. The next slide says the big idea. Even if energy is not conserved in a collision, momentum is always conserved for both elastic and inelastic collisions. Okay? And with that, we will begin looking at conservation of momentum problems in the next video.